Hello, everyone, and welcome to Talk Nerdy. Today is Monday, May 18th, 2026, and I'm the host of the show, Dr. Cara Santa Maria. And as always, before we dive into this week's episode, I want to thank those of you who make Talk Nerdy possible. We use Patreon as our portal for supporting the show. If you're interested in making a per episode donation, all you've got to do is visit patreon.com. That's patreon.com/talknerdy. This week's top patrons include Chuck Blell, David J. E. Smith, Daniel Lang, Mary Neva, Will Dufresne, David Compton, Brian Holden, Gabo J., Ulrika Hagman, Pasquale Gelati, Rika Maharaj, and Joe Wilkinson. It's because of you and many, many others that we're able to keep making this show all the way, since 2014. Today's episode is episode 602. Thank you. Thank you. All right, so let's get into it. This week, I had the opportunity to chat with Dr. Emma Chapman. She is an award-winning astrophysicist. She's a Royal Society Research Fellow and lecturer based at the University of Nottingham. She's received many, many commendations and prizes, including the Royal Society Athena Medal. Her first book was called First Light, and she has a new book out in the UK. The title is Radio Universe, but here in the US, it is called The Echoing Universe, How Radio Astronomy Helps Us See the Invisible Cosmos. So without any further ado, here she is, Dr. Emma Chapman. Well, Emma, thank you so much for joining me today.
Thank you for having me. I'm really looking forward to having a chat.
Absolutely. So we're going to be talking about your new book, The Echoing Universe, How Radio Astronomy Helps Us See the Invisible Cosmos. And like I usually do at the very top of the show, before we dive into any sort of specific content, I like to get a little bit into process. I'm curious about your kind of career trajectory, how you found yourself in astrophysics, what you studied in school, and if it was sort of like a linear path or if there were some twists and turns in there.
I'm going to say linear chaotic.
I like
know
that.
If that's a thing. But I've been on a straight path, but it's been very wiggly. So there's been, I did not grow up loving space. I will say that straight away. The first time I owned a telescope was I was about 34.
Oh, wow. Okay.
Only a few years ago, believe it or not. So I've been a professional astronomer for far longer than I actually ever owned a telescope. But I did grow up loving history. And I really, really wanted to be an Egyptologist. So I did all of my work experience in Egyptology, packaging 5,000-year-old shoes into little acid-free paper cardboard boxes.
Wow.
In a very famous museum in Oxford. And then I picked up a book in the library that was about something called special relativity. And all I really remember, I was about 15, and it had a blurb about, hey, this is about time travel and how the faster you move, the slower you age. And I genuinely thought somebody had put it in the wrong section and that it was a science fiction book. So I took it home and I didn't understand 99% of it. But I did understand that I wanted to understand it. Yeah. And almost overnight, I switched all my options to study physics.
I love that.
Yeah, it's what I try to tell high school students now when I give talks is that, you know what, if you don't know what you want to do right now, that's fine. Like, you can have a few left turns in your life. That's okay. And yeah, even then, I went to university to study physics. I still didn't have a real interest in space until again I found out about the way we can explore the Big Bang and the era of the first stars. And then that little kid who had been fascinated by history and wanting to explore tombs in Egypt suddenly went, well, hang on a minute. that's history.
Yeah.
Yeah, but of like billions of years as opposed to
Really old.
a few
Yeah.
thousand. And I was like, wait, nobody's dug up this time. Nobody's explored this first billion years. Well, how do I do that? How do I do that? And so I started a PhD, and I was told that the only way I could do that was using radio telescopes. And so I gave myself a very quick crash course on radio astronomy during my PhD, and I've never looked back. And yeah, I like to tell people it's a bit twee, but that I'm still a historian. It's just that I've swapped the trowel for a telescope.
Absolutely. And I mean, so many things come up even as you're sharing your story. One that is sort of in the front of my mind has to do with the way that we structure academia. And obviously, the structures are pretty different between the US and the UK, but there's still a lot of crossover. American students can go study in the UK and vice versa and still, be on the right path and get the degrees that they are setting out to get. But one thing that I do notice is that especially at the undergraduate level, and of course, even worse as we get to more specialized graduate training, I worry that we don't do a great job of introducing these topics from a top down approach first and then getting into the bottom up training. I worry that so many kids are subjected to fundamentals of physics before they ever understand why we want to learn physics, that they are turned off by the I don't know, not being able to connect the dots between, let's say, learning the mathematics and understanding that, yes, this is like a historical enterprise, for example.
Yeah, I agree completely. There's so much I could say on this, but it comes down to you need to inspire. People need to
Mhm.
feel inspiration and awe. Awe's a big word I use a lot. Is that it's you need to feel that awe, that like, wait, I just don't understand this, but I feel something deeply. That
Mhm.
feeling is what I try and kind of inspire in younger people for exactly that reason, to be like, hey, look, our physics curriculum, I don't know about the US particularly, but in the UK, is really quite dry. It's all,
Mhm.
right, we're going to learn about simple harmonic motion and this and that. And oh my God, no wonder I wasn't planning on studying physics. And it took a popular science book for me to be like, wait, I'm sorry, time travel? What? And that's what made me do it. But I think there's a bit of kind of almost, is it snobbery or gatekeeping? I'm not sure what the right term is, but I think it's that people want to feel like they're super smart once they've done all of this training and they do understand general relativity. And they're like, well, I can't possibly explain it to a 13-year-old. I'm like, well, no, you could actually. It's just that you don't want to lower yourself as you see it and break
Yeah.
down that theory to the exciting fundamental blocks. And that's how I write, actually, is very much is kind of the second part of that question you asked, was kind of like the process of me becoming an astrophysicist and in some way an author on this. Is that's how I understand science. If somebody comes to me with a scientific theory now, I still to this day can't absorb that 100% and go, oh yeah, it's very, very clever. I have always been the one in the room that is absolutely willing to ask the air quotations stupid question.
Right.
Because otherwise you can't advance. And so what I always do is I go back to when that theory began, and I like to read and watch how that theory evolves over decades. And that's how I understand something, is by breaking it down. But you're right, unless you have that knowledge of what's going to come, what's at the end of this journey,
Mhm.
yeah, you know what? It can look a bit dry at the start because you don't know where you're going. You need both
Yeah, and
sides,
it's
and you
hard to
don't.
not see that light, right? The light at the end
Yeah,
of the tunnel, to help you get through the slog sometimes.
for
I think
sure.
that I see a similar, I don't know if it's a character trait or if it's just an insight, really. I think that's it more than anything. It's a similar insight amongst my peers and colleagues who work as both scientists and science communicators, or individuals who, write kind of trade publications, books for public consumption, or do television or podcast, that they see that there is that disconnect. And I think about the fact that I had a friend. He's an older adult, so which will matter as I describe this, but he was lucky enough because he was a non-major when he attended university at Cornell. He took a course from Carl Sagan called Physics for Poets.
Oh, my Lord.
Can you imagine? That probably was the quintessential course that does exactly what we're describing here. Inspires awe and wonder and assumes you guys aren't going to become professional physicists. So here's some of the stuff that you need to know in order for all of this to make sense, but we're not going to get lost in the minutia. And I wish we treated all young physicists as poets.
Absolutely. And all poets, like as physicists and physicists as poets, it's this old idea that you can send people to Artemis, or you can send a probe to the moon, that's very different from having a human on board, especially someone who's got an artistic or poetic disposition and is able to describe that in like a language that humans can understand. And I think when it comes to this kind of, to extend the analogy you just said about the light at the end of the tunnel, you need to see it. To see the light at the end of the tunnel, you can't have a lot of stuff in the middle. And that's where science communication comes in. It's about removing the stuff in the middle. You need to give them the inspiration, the light at the end, and you need to start them on the journey and give them the means to get through that tunnel. But if you keep it blocked up with all the equations and all of the this and that, and we must be fair to include exactly this. And it's like, do you know what? Forget your caveats sometimes. Sorry. But what's important is this feeling that you inspire into people, and that I guess that you help reduce their fear. You help reduce their fear so that they can go on, and then the next time they come across something with the title radio astronomy in, for example, they'll be like, oh, actually, do you know what? I am smart enough to read this article. I am going to give that a go.
Yeah. And, I think radio astronomy is such a perfect example of a topic and an area of inquiry where you do have to dig a little bit deep to find that way in. And the reason I say that is because when we think of popular science communication, especially now that everybody is on their, cell phones and everybody is connected to social media, one of the ways that I think NASA has historically, for example, had such a wonderful public outreach effect is through imagery. And very often that imagery is it's visual. It's like the visual spectrum imagery. And so I talk to astronomers from time to time on the show who are working within spectra that aren't as readily understood to the eye. And so I'm curious if maybe you can share with us right at the top, what is radio astronomy? Like, what tools do you use to detect it? And what does it look like physically? Like, can you print it on paper? Do you approximate it with visual representations?
Sure. So radio astronomy, it puts together two terms that we're really familiar with. One is astronomy, which is the study of the universe, literally looking up. And radios we're used to in our daily life. The older of us will have remembered actually having a physical radio with an antenna, whether on our car. The younger of us will may be surprised to know you do have radio antennas, but miniaturized in your phone. And what those are doing are collecting a type of light. So optical light is one part of the whole spectrum of light, but the really longer wavelength, low energy light is called radio light. And that's so good at communicating. It's really good at keeping information and not getting kind of disturbed by the atmosphere of the Earth or clouds or all sorts of things. So that's why we use it to broadcast on radio stations, because it's just really good transferring information over long distances. So radio astronomy is putting those two things together. It's looking up and communicating. It's looking up and listening, and sometimes sending radio waves out into space and echoing them back and seeing what information we can get when we listen back. And to do
Mm.
that, I use the word listen. I use the word listen loosely here. And that's because when we think about radios, we think about listening. But what it really is seeing. And so we need to build a different kind of eye. Now, our eyes are evolved to see really, really small wavelength light. So you can kind of just really imagine like drawing a wiggly line that's really, 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 really wiggly.
Mhm.
But the radio waves is much broader wiggles, and you need a much bigger eye to be able to do that. And the thing that works for us is a big metal antenna. So what happens is we use an antenna that you might even have on the side of your house, rusting from the days of satellite television. What you might have something that looks a bit like a kind of spindly Christmas tree on the side of your house, or you might have a satellite dish. Both of those are radio antennas. They are both able to receive radio waves, and they're both able to receive radio information from the universe. So you could call them radio telescopes as well. And that's kind of what it is. It's using this antenna to gather radio light and then translate it into something that we can understand as humans. So the way I like to think about that is a paint by numbers. So if
Okay.
if anybody's done a paint by numbers with their kid or by themselves, I'm not judging. You have like these images, and they'll be broken down on a canvas where it's kind of got like all of certain parts. We'll say 1 is red, 2 is green, 3 is blue, and you'll have a set of paints, and you'll paint all of the number ones red, and eventually you have an image. Now that's all we do with any wavelength of light that we're not evolved to see. So it's almost like we take the rainbow and we shift it to the radio wavelengths, and we say, you know what? A 2-meter wavelength radio wave, we're going to call red. And a 2.5-meter wavelength radio wave, we're going to call blue. And we
Mm.
colour the image that we're getting in like a paint by numbers. And then it's just that image looks like any other kind of image that we might see in the optical light. And I'll just finish by saying that layer of translation, you're right, does seem to provide an obstacle. It does
Mm.
seem to be like, oh gosh, this is a little bit hard, until you realize that actually the optical images you see from Hubble, for example, which is an optical telescope, they have also been translated. They have been observed in different optical wave bands like red, green, blue, and they put them together in a
Wow.
certain kind of way. So that layer of translation is always happening. It's just people are more fearful of it when it comes to something like radio astronomy, which is just that touch less tangible.
Right, right. Just beyond what their eye can see, but the data are still there. And I think that's the important kind of point here, is that, you were describing these dishes on the side of your home. I have a dear friend, Dr. Summer Ash, who's been on the show before. For anybody who remembers way back when, I'm probably due to have her on again. And for years, she was a staff member at the National Radio Astronomy Observatory. And so she actually managed all the tours and the visitor experiences at the Very Large Array, which is very close to me here in Los Angeles. It's in New Mexico. And so this is I think what people usually, at least in the US, I think if you have heard of radio astronomy and an image comes to your mind, I think it's probably the Very Large Array that comes to your mind. These massive satellite dishes that are actually telescopes.
Yeah, that's really interesting. I'm so jealous to start with. But that's really, I hadn't actually thought about what image might come to you in the US actually, because here it's Jodrell Bank, it's the Lovell telescope, which is
Mm.
big, kind of 300-foot-ish, 200 feet, I think, diameter dish. For me, it's always Arecibo in Puerto Rico
Mm-hmm.
that comes to
Mm-hmm.
mind. This massive dish that was 300 meters across.
Wow.
But what those instruments do is just this level of translation from light to electric signal. And that's
Mm.
exactly what our eyes do. So this light comes in through our pupil. Sorry, I was struggling there. Comes in and it hits the retina, and it produces an electric impulse in the retina, which then goes on to go down the nerves into the brain and is translated into an image that we can, understand a little bit more. And that's what an antenna is doing, is the radio light is falling on that metal. It's introducing an electric voltage or current, and that current is then going, that voltage is going down your cables into your computers, and it's being translated into, okay, that means it's that bright in that wavelength over there. And that's all we're doing. And we might steer our telescopes in different ways. We can get into the weeds of that a bit later if you like. But you can have these dishes that kind of point in different directions, like we turn our head. You can have a little bit more clever stuff like the VLA, the Very Large Array, which can plug dishes together, telescopes together, and create the equivalent of a gigantic telescope as well. There's some really cool stuff that you can do just with radio astronomy.
And there's also, I think, when it comes to the data itself, like what we are actually observing. You mentioned the comparison. You did such a beautiful job of describing to us what those radio signals are and how they do differ from optical signals and how we can sort of translate and interpret that data. But of course, that means that with radio astronomy, you can, quote, see or hear things that you can't see with just visible light. Isn't that true?
Absolutely, yeah, and it is the same with any wavelength. I try not to get too tribal about it.
Right, that's true.
but like, I do absolutely have a soft spot in my heart for radio astronomy, obviously, which is why I wrote the book, because I do find that it is underreported, let's say, because of people's fear of it. And what amazes me is that even though I'm a cosmologist by trade, my area is the first stars, first black holes to exist in the universe, I have always had a really strong interest in other areas of astronomy and actually all popular science. I read a huge amount of popular science across the board, always have. And I was fascinated that I just kept reading these books that had nothing to do with radio astronomy. And there'd just be a throwaway sentence saying, oh, and actually, yeah, the first exoplanet, the first planet outside our solar system was found by a radio telescope. But, oh, okay, I didn't actually know that. And then, and it would be every area that I'd come across that radio astronomy had kind of just been quietly getting on with it. And not really enjoying much attention, I suppose. And so there's many things that radio astronomy can look at. It's looking at different physical processes. That's the way we can think about it. All the wavelengths of light probe different physical processes. So the James Webb Space Telescope, it's really good at getting through kind of the dusty parts of our galaxy and looking at stars being born. It's really good at that. Radio telescopes, radio waves, as I've mentioned, their superpower is kind of being able to travel unperturbed, which means that they can glide not just through our own atmosphere, but through, for example, the atmosphere surrounding Venus, which is entirely impenetrable to optical light. We've never seen the surface with optical light sent from Earth. We've sent a few probes down there that have been horrifically crushed after 30 minutes, but just before they die horribly after 30 minutes, these metal probes, not crude, I should be very clear, they have sent back 12 images, and that's all we've got. Whereas radio waves, we can, from Earth, press a button, send some radio waves along. A few minutes later, it'll bounce off the surface of Venus, having just slid through that almost impenetrable atmosphere. It'll come back, and we will get these incredible 3D renderings of the volcanoes on the surface of Venus.
Wow.
And yeah, that I could go on, but I don't know how much you want me to talk about it now. But my absolute favorite in the solar system is ice on Mercury. So that blew my mind. I could not wait to share that with people. I found this out and I was like, I have to write about this now, because I literally felt like coming out of the pub and tapping people on the shoulder and be like, excuse me, did you know there is ice on Mercury? I was like because I feel like you should not go home not knowing that. And it became this compulsion in me to tell people. And like, this is why I write, is so I don't alienate all of my friends and family, because I just tell my word processor instead.
And so the only way that we know that is because of detection with radio.
Yeah, because where you can't kind of shine a light, an optical light on something, you can't see it with an optical camera. And Mercury has some really deep craters, and parts of its surface never ever see sunlight because of this weird way it rotates.
Mm.
It rotates so weirdly that actually the sun sometimes comes up halfway, goes backwards, and then comes back up to finish a sunset. It's really very strange. But anyway, there are places that optical light just cannot get in, even if you're right up close. And so radar, what that can do, radar, by the way, is just the method of sending radio waves and them
Hmm.
echoing back towards you, and you listening to how that echo is changed to work out how big the cave or the crater is in this sense. And what happens is when that light bounces off the bottom of a crater, usually it would come back and we'd be like, okay, this crater's about this big, this deep, fine. This light came back ever so slightly changed in its kind of direction of waviness, we're going to call it that, but polarization, like the direction that the wave is traveling, kind of 90 degree. Oh my God, I'm not sure I can be bothered to get into this right now unless you ask a follow-up question on that. But like because honestly, you know what I said earlier about the caveats, let's just, you know what the cool thing is here, not the polarization, is the fact that the light came back changed, and it came back
Yeah.
changed in such a way that it could only have been reflected by something really shiny and frozen like ice. And yeah, sure enough, they then knew what to go look for with other probes, and they confirmed it was indeed water ice on Mercury from comets millions of years ago that has sat there frozen on the
Ugh.
hottest planet. Well, not the hottest planet, but the closest planet to the sun,
Yeah.
in incredible temperatures.
That's amazing. I mean, the fact that it's not just about sort of tools. Obviously, these are tools that are used to answer questions. I think science is interesting in this way because sometimes when I talk to folks who aren't scientists, I notice certain assumptions that are completely reasonable assumptions, and I'm going to take a hard left turn to explain or to prepare for the discussion that I'm teeing up here. I'm remembering. So I'm a psychologist and I work in a cancer center, and I'm remembering talking to a patient who had a very rare kind of cancer, but that very rare kind of cancer has all of these really like cutting edge treatments available that are, nearly curative and just very, very almost sci-fi in nature. And I remember this patient asking me, like, why would they have that for what I have when so many more people have, breast cancer or
Mm.
prostate cancer, all these different types? And I was like, oh, right. Because sometimes in science, we ask questions and then we go try to work to find answers. And other times in science, we are asking broader or somewhat related questions, and then we stumble upon things where we're like, you know what that would be good for? You know what that would probably help us? And that's why certain cancers have certain treatments available that feel light years ahead of others. It's because somebody stumbled on some genetic quirk or some cool way that the cells were reacting to something in the lab, and they go, oh, this actually isn't working for this solid tumor, but look what it can do in the blood.
Mm.
And I'm curious. I mean, I can only imagine that physics, and especially astrophysics, works in a similar way, that sometimes it takes those really innovative minds who were working so hard and so narrowly to solve a problem, but then said, I wonder what would happen if I apply this technique to this question over here, and then something breaks wide open.
Absolutely.
Yeah, like what kinds of questions has radio astronomy been able to answer in that way?
Yeah, I'm going to give you the list in a minute, but just to like comment on that question, is
Yeah.
like, I couldn't believe more. You, how do I put this? People will often talk about a serendipitous discovery, as in
Mhm.
like, oh, it just came out of nowhere. That's very rarely true. It's
Mhm.
exactly what you describe, is that somebody was trying to ask a broader question. They had the education and the curiosity is absolutely key, I think, to answer that question. But that curiosity carries them further than the knowledge, than the
Mm.
education, because it's that curiosity which, when you find a radio signal like Jocelyn Bell Burnell in the 1960s, and she's sat there for months looking at a printout of what is basically a straight line with some wiggles on. And she's looking for one kind of wiggle. And over football field length pieces of paper, she has the curiosity to notice a very small, different kind of wiggle. And most people would have walked away. Most people would have said, that's not the wiggle I'm looking for. I'm not interested in this wiggle. I haven't got time for this wiggle. I want a PhD on the other kind of wiggle. Yeah. She said, wait a minute, that's weird. Hang on, what is that? And everything stops. And she has the curiosity to look. And she finds, after a small amount of time, finding that this signal is repeating. And it's like, what is this signal? Is it aliens? And they famously wrote LGM in the margins of this printout, being like, could it be little green men? Until they realized there were 4 on the sky. And it was very unlikely that aliens were communicating to them from 4 different areas at the same time. And they eventually found that this was a completely new kind of astronomical object called a pulsar, which was a spinning neutron star. So a star that has collapsed at the end of its life to such a compact little sphere that it's only about 10 kilometers in diameter. So a star, but about the width of a city. Small city, completely composed of one type of particle called a neutron, and it's spinning so fast, it's spinning thousands of times a second, and in doing that it triggers a physical process where beams of radio light come out of it like a jet of like a lighthouse beam, and that beam is passing over Earth, and that is creating a wiggle in Jocelyn Bell Burnell's radio telescope, where she was least expecting it. And if she hadn't have been curious and open at that moment, and I'm going to get political slightly here, hadn't had the funding and the time to be able to explore that. It's so important in science to give people time to study this curiosity-driven research. Then you know what? Pulsars wouldn't have been discovered in 1967, I think it was. They would have been discovered in, let's say, 1975, 1983. It would have happened. It's just you need both the knowledge and education and the curiosity and the time to be able to do that. So
of before you continue with the more examples, I guess, from radio astronomy, I feel like that is a point that so bears repeating when you said, I'm going to get political for a second. Obviously, it speaks to exactly this concept that so many people in, I think, positions of political power who have the power of the purse, who are sort of setting policy on who gets funded and who doesn't and where we spend our tax dollars, they are thinking, and not nefariously, simply, I think, naively, that the way to answer questions in science is to make sure you are asking the correct question, to fund the thing that we think is the best, current way to investigate the thing, and then to report on those results. And that, the truth of the matter is a lot of discovery comes from interdisciplinary collaboration and conversations and crossover, and having exactly what you said, the empowerment, which comes from privilege. It comes from funding, it comes from backing, and it just comes from like having, people in positions of power to say, yeah, you have, you are empowered to do this thing, to be able to chase down a side quest from time to time. Because if we didn't have that latitude to do that, everything would be siloed. And we would have a bunch of false stops and starts. And actually, I think that the political machine would become disillusioned because they would say, no, we funded you to do this thing and you couldn't do it. So clearly you're not the right person for this, or this lab is not the right lab, or you guys aren't good at your jobs. Well, sometimes we just can't do certain things because we don't have the technology yet, but we have other things that not being able to do that thing taught us we could do.
Absolutely. You can use the technology that you didn't expect at the start of the grant, for example, to suddenly do something else. Or, if you're expected, sometimes people think that they want a question answered and that there should be one group of people that are best tasked to answer that. That's
Yeah.
not true. You have to have people working all the different little parts. And then, you know what? Trying every combination. It's a buffet. You're going to try every combination of things to make something work. And the temptation to seek a shortcut. And you're right, it's not nefarious. The people don't want to waste taxpayers' money. They
Of
shouldn't
course.
want to waste taxpayers'
Yeah.
money. What we fail to communicate sometimes is that they are wasting taxpayers' money by seeking these single solution questions. We're undergoing what are quite catastrophic cuts to UK science at the minute, as I'm sure you know. I'm sure you
Oh yeah,
share the
same here.
pain, share the pain, so you understand this. And we're trying to communicate with people that are really trying to do the best by their constituents. That actually, you know what, that you need curiosity driven science, and it's not. It's not a case that by allowing people that space to do the side quest, I love that, to pursue the side quest, that you're giving them a blank check. No,
Right.
we're not saying, hey, you go do your thing and book first class and do whatever you like. We won't check on you. Not at all.
Mm.
We're saying, here's some money. Here's your main quest. Yeah, sure. You know what? Have some side quests, and having the confidence in those people that they are going to do some wonderful science, and it might not be what you expected, but it is going to be darn good.
Yeah, yeah. And it's going to make some sort of difference. And I think that's where the communication of science, not to go off on a complete tangent, but the public communication of science is so fundamental to the scientific enterprise. And while I am somebody who agrees wholeheartedly that there are scientists who are phenomenal scientists who probably shouldn't be the people that we are putting out in front to communicate their science, I don't think that a lab should exist on the planet where there are not individuals whose entire, maybe not their entire career, but their a portion or their entire emphasis is being able to communicate what is coming out of that lab, both for other scientists, but also for policymakers and for the public. Because if we can't do a good job as scientists to get people to understand why what we are doing matters, it is all done. It's a tree falling in the forest. Like nobody is going to be able to justify continuing to fund it. And the public is going to become disillusioned, and they're not going to want their taxpayer dollars to go towards that funding. And I think part of the problem sometimes is that there are fields like biomedical science that have done a phenomenal job of saying, look, this directly impacts you. If you don't help us work in this Alzheimer's research, you personally may suffer in the future. And I think it can be more difficult when we talk about questions like, what is the origin of the universe? But these are also very existential questions. And I think people like you are so important in your fields because you take the time to say, this is why this matters.
Yeah, I think it's that I'm reminded of a time I visited Stanford,
Mm-hmm.
and I visited Stanford once in my life. I do not come. I come from like a middle class kind of UK family, so like we did fine, but we certainly weren't rich. We had to
Mm-hmm.
watch money and everything like that, and I certainly would have never been able to go to kind of like anywhere like Stanford.
Yeah, yeah,
So
yeah.
I was so scared when I went, and this was only like 5 years ago. Okay, so well into my career, and I was still that intimidated by everything I'd heard. And I got there, and yeah, do you know what? I was so intimidated, and I was thinking, oh my gosh, people are just going to be awful. And then I found out that this astrophysics department in Stanford hired full time a science narrator.
Mm.
And I was like, I'm sorry, what is this? And I had never come across this. And it was the most wonderful thing. This whole department was completely versed in the fact that they would do their amazing astrophysics research. And then there was this person who had done astronomy research previously, but had like also like a really good like science communication background. And their job was to listen to this scientist and go, okay, no, this is the narrative of what
Mm.
you have studied. And it is about picking out exactly what the problem is that they have moved towards solving. And I always come away from that because I went with such of my own prejudice. I was so afraid, like I was so scared of being kind of the victim of like this
Right.
prejudice. And I went with my own thinking like, oh, these like super rich universities, that they're not going to care at all about science communication. And actually, I've taken that lesson back to all of like the lesser privileged universities that seem to think we must do pure science to be respected. And I'm like, no, no, no. Do you want to know what they're doing?
Mm,
They know this matters. They know that this is how they get more funding. They
yeah.
know that this
Yeah.
is how they do public good as well. And you're right, it is hard in astronomy. It's both easier to be in astronomy because people love space from like the minute they understand it, right? 4 years old. They're
Right.
like,
It's kind
oh
of
my
like
God,
space
yeah.
and paleontology kind of already have
Exactly.
that built in.
It's
Yeah.
space and dinosaurs, exactly that. And so we already have that people are naturally like, oh, wow, tell me more. Also, they don't really want to listen after 5 minutes. So you'll tell them something amazing about black hole, but oh, that's amazing. But then they'll go around their day and they'll not understand that, let's say, some of the technology that's used to develop the telescope has actually been used in retinal implants because we're so good at detecting incredibly low levels of light in our telescopes
Mm,
that we've managed to transfer that technology into that kind of medical application.
yeah.
Nobody wrote a grant saying, I'd like to study dark energy and also solve the problem of partial sight. Like,
Yeah.
like no, it came out of it. And there are, plenty of things, plenty of examples like that. But it's both harder and easier.
Absolutely. I'm curious, kind of going back to this opening conversation about what is a radio wave and how do we detect it, and you told this wonderful story about the discovery of pulsars by this blip on radio wave data printouts that was not what was being originally observed. What other things about our universe? I mean, obviously, I can imagine that it's like pretty much name an aspect of inquiry, and you can identify what radio waves have helped us understand. But you mentioned, for example, that personally you were interested in the early universe, kind of the immediate uh, outcome of the Big Bang and what was happening kind of when everything was very hot and not very differentiated. And I'm curious, what does radio astronomy tell us about a really long time ago?
Well, that is a difficult question for me to answer because at the moment we're still in the very early stages of exploring it.
Mm,
We have started building these incredible telescopes like the Square Kilometre Array in the Western Australian desert. 130,000 antennas we're going to plug together eventually.
wow.
And the reason we're doing that is because very early in the universe, it's very hot, it's very chaotic. Nothing much can form apart from hydrogen and helium, the two lightest elements there are, hydrogen and helium. And eventually, over tens of millions of years, this begins collapsing into the very first stars, which were completely different species to the stars that we see around us today. They were 100 times the mass of our sun. They were bright blue. They were really astonishing objects. And what they did in that era was they kind of heated and changed all of the rest of the universe, all of the hydrogen lying around, and it emitted radio waves.
Hmm.
And those radio waves have been traveling to us for 13 and, change billion years, 13.8 billion years. And as I said right at the beginning of this conversation, if you want information to last a long time, what do you use? Radio waves, because they are
Mhm.
the ultimate communication device, basically. So, yes, did a lot of stuff in the early universe give out UV light, optical light, infrared light? Absolutely. It's all there. It's just that we can't detect any of it anymore. Whereas the
Mm.
radio light are like the hieroglyphics on the walls of the ancient Egyptian tombs. They have these ancient messages which were written over 13 billion years ago, and we're just uncovering now. And so
Yeah.
our job is to get those radio waves, and looking at those, what we will be able to work out is how many of these first stars were there, because we've never seen this kind of first few 100 million years of our Big Bang. We've never seen the first stars. We've never seen the first black holes or the first galaxies. And we'll be able to work out, okay, well, how many of them were there? It's like working out how many dinosaurs walked the Earth. We know they were there, but how many were there, and when
Right.
did the
Yeah.
first black holes come first? That's something really recent. Totally upended our understanding. We thought the first stars came first, collapsed into the first black holes. Now, with the early kind of data, we're starting to think actually it's the other way around, and the first black holes formed alongside the first stars. Which is just a fascinating area. So yeah, that's what we're trying to work out, and doing that, we're going to be able to create images of the early times, hundreds of million years after our Big Bang, but like the first billion years, let's say. Let's round it up. The first billion years of our Big Bang, we'll be able to actually create an evolving image of these radio waves, and that will
Hmm.
tell us how it's changing over time. So it's like going onto Netflix and streaming, like a live action film of something going on for a few hours and working out. And that's what we're doing. We are streaming the universe. We're downloading like a historical documentary, historical footage of our universe growing up, and watching it, being able to press fast forward and watching it over that billion years. When did the first
Yeah.
stars come? When did they die?
Oh, that's fascinating. And so, is this one of the areas that you were digging into for your dissertation?
Yeah, this is exactly my area. It's the area that my first book was written about. And yeah, so this is my bread and butter. Is what I studied. My job specifically is to kind of use these really huge radio telescopes. I use one in the Netherlands to try and get this radio signal from the cosmic dawn, that we call it.
Mhm.
The problem that we're trying to solve is that signal's really faint. As you can imagine, you try
Yeah.
shouting, it's a few tens of meters before somebody can't hear you, right? You try doing that over 13 billion years of distance. It's a long, long way.
Yeah.
So my job is to dig that signal out, like the archaeologist I always wanted to be, from something 10,000 times brighter, which is our own galaxy. And it's really hard, which is why I'm still doing that about
Yeah.
15 years after I started to dig. But we're getting ever, ever, ever closer. So it's really exciting. It really is like just one of those little brushes, kind of like, dusting away one layer at a time of dust.
Yeah. So I'm curious then, that leads me to wonder, as you're putting together this most recent book, you've obviously been studying radio astronomy throughout your career. You are a radio astronomer. You've been digging deeper and deeper into this, kind of time in our universal past where there are so many more questions than answers right now. Uh, you probably already knew quite a bit going in, but of course, in order to write a book for public consumption about a topic, you want to be somewhat thorough. You want to ensure that you're, doing research in areas where maybe your understanding wasn't there. Is there anything that you discovered? I mean, I think that you already gave us a beautiful example with the ice on
Mhm.
Mercury, but were there things that you came across, or maybe you knew them, but you were like, oh, I forgot I knew that, or like, wow, I can't believe I didn't know that about radio astronomy that surprised you?
Every chapter. And that might undermine my authority. But I don't care. I once had a publication when I admitted that in print. This was years ago for a different thing, but I been like, oh, I actually didn't know much about this going in. They were like, our readers do not appreciate knowing the same amount as our experts. One must provide an air of expertise. And I'm like, no.
Okay.
Like, you know
Jeez.
what? I think we're done here. No, I will admit that, I knew the headlines. Of course I did. I am a radio astronomer. What I discovered again and again and again is that I didn't know how rich this history was, and how some of the major discoveries, like the one that comes to mind after the ice on Mercury, is that the first ever planet outside our solar system was discovered using radio astronomy.
Mm-hmm.
The reason it's
Wow.
forgotten is because it was around a pulsar, which luckily I've already talked about today, which is this spinning neutron star. The reason that was quickly forgotten was because we're very human centric and life centric, and when we're looking for planets, we want them to be habitable because we want to find aliens. And so you can't live around a pulsar because the radiation is ridiculous and it's a dead star. So we wanted to find an exoplanet around a sun-like star. So the minute that happened, it's like the radio one didn't exist. But the technical ability of being able to do that. And so, going into this, the pleasure of this book was starting from exactly the point you say, which is like, hey, I'm a radio astronomer doing cosmology. I'm going to write a book about like that kind of stuff. Oh, what else can I write about? Right, solar system. Honestly, I started writing this book where the solar system was 1 or 2 chapters. As I dug, I was like, my God, this is part 1 of 3. Like this is half the book. I need to go planet by planet here because I had no idea it was that rich. Like again, I knew the headlines, but like, it got me again and again. And I'm such a nerd for the actual instrumentation itself. I think because I feel like I owe it something. By instrumentation, I mean the actual telescopes, because the first time I ever saw a radio telescope, I was deeply disappointed. I was like, are you kidding me? Like, I've got to spend 4 years in a really flat, wet place in the Netherlands where all my optical colleagues get to go to Hawaii. Like, are you kidding me? Like, they literally look like TV aerials. And then that completely flipped just after a few months, and I realized that wait, with just a few TV aerials, we can look back to the first stars. Damn, we're smart. I was like, and so like I'm a real nerd for kind of just explaining to people that you know what, you look at it and you might be like, that's not as kind of cool as a rocket launch and like, flying to the moon and everything. It's like, but I just want you to spend 3 minutes thinking about the fact that somebody can send some radio waves, boil a kettle, and come back and have answers about Venus that
so
no
amazing.
space probe was able to answer. And I think the breadth of radio telescopes as well always amazes me. So like a lot of optical telescopes will kind of be designed to look at galaxies or to look at this. Radio telescopes, they tend to be, do you have Swiss Army knives over there? I'm not sure what you'd call them. If not, okay, good.
And we call them the same thing. Yeah.
Okay, good. I don't know why I didn't assume it because they're Swiss and I'm not Swiss, but anyway, whatever. The Swiss Army knife of telescopes, basically, like pretty much any radio telescope is able to look for aliens while checking for pulsars, proving general relativity, looking at the central black hole of our galaxy, which incidentally actually is how the whole of radio astronomy was invented in the 1930s. We talked about serendipity earlier. It was about this guy called Carl Jansky putting on some headphones basically and hearing a hiss over this telephone line and being like, hey, I wonder what that hiss is, and building this antenna that could look at the sky.
Wow.
and he found out that was actually, that hiss was coming from the central black hole, the supermassive black hole at the center of the Milky Way. And in 1933, which is, that's how it all began.
That's incredible.
So
and
we're
now,
very
of
young.
course,
We're very young
yeah.
field.
I mean, and at the time, like questioning even the existence of some of these like cosmic kind of objects and do they exist even? Are they theoretical? How can we measure them and detect them and continue to collect evidence for their existence? Like what a cool thing to be involved in a field, in particular endeavors within that field where there are so many brilliant and innovative people using so many just interesting tools to to try to answer similar questions from different perspectives, where at the end of the day, you can say, we're pretty confident that is what's happening here, that there is a giant black hole in the middle of our, solar system, or in the middle of our galaxy, because or actually in the middle of the galaxy. Are there a lot of them?
There, there are so many, you're not going to sleep at night if
There
I
you
tell
go.
you there are black holes roaming around our Milky Way quite happily. But there's one supermassive one at the central,
Right in the
central
middle.
area. Yeah.
Yeah. And so in the middle of our galaxy, this supermassive black hole that was, at one point in time, highly theoretical in nature. Now we're able to say, because of these measurements and those detections and these equations and those observations, we were able to freaking image a black hole recently.
Using radio waves.
There you go.
Just gonna pop that in there. People think that image was optical. It was not. It was radio waves.
Phenomenal. And now I think 2, right? We've imaged 2.
Yeah. Yep.
Oh, that's so cool. I mean, that's what science is really all about, right? It's about saying, I'm just sitting back, feeling the vibes, noticing that something feels peculiar or interesting. How do we explain this? How do we describe this? Let's build some stuff. Let's start to investigate and interrogate. Oh, you over there, you want to try it that way? Cool, try it that way. And then at the end of the day, everybody gets together and goes, your thing and my thing and their thing.
Yeah.
Seems like maybe there's something going on here. And what a cool thing.
Yeah, and the universe is the biggest laboratory that you can find. Is that, you can kid yourself that maybe, astronomy is the pretty subject. It's like, no, excuse me. you can't find magnetic fields that are more intense than around neutron stars and black holes. You can't find denser matter than is near a black hole. You can't find hotter temperatures, colder temperatures. Nuclear fusion could solve the energy crisis on Earth. Do you know the only place we've seen it work? In a star. So for me, I think just bookending this conversation, you asked how I got into this. I very much came into this not as somebody who loved space. I do love it. As certainly as increased as I've got older, but I do love it. But I came into it as a physicist, wanting to test the frontiers of our understanding of our universe. And that goes to the very small as well. So general relativity, quantum physics, condensed matter physics, all these crazy terms that you can test by looking at this massive laboratory. And there comes a level of patience with astronomy as well, where, your line of work and a lot of different places will have laboratories where they'll set up a hypothesis, they'll test it, right? We can't always do that. As astronomers, we can't say, hey, I want that star to explode tomorrow because it's during my grant. We have to be quite creative about working out where to look and when to look and how to combine data to get to the answers we want. And it's that ingenuity that I really enjoy in astronomy broadly, but especially in radio astronomy, where you have to go that step further because you don't have the intuition of your optical senses.
Yeah. Oh, gosh. So many fascinating stories to continue to tell, and so much, awe and wonder to inspire in us. And hopefully for those listening, their appetite has been whetted a little bit to be able and curious to dig even deeper. And should you do so, the place to start is with the book, The Echoing Universe, How Radio Astronomy Helps Us See the Invisible Cosmos, by Dr. Emma Chapman. Emma, thank you so much for being here with us.
Thank you.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.